Okay, so I think we can begin. So welcome everybody to the public PhD defense in computer science and engineering for Sahar Tahvili. The title of the thesis is Multi-Criteria Optimization of System Integration Testing. And my name is Marcus Bolin. I am the main advisor of Sahar and also the chairman of this session today. I should also say that the research has been conducted at the RISE 6 Västerås office here in town in collaboration with Mälardalen University. The supervisors of the research has been me as the main advisor. We have Vasif Afzal from Mälardalen University and Merdad Sadatman from RISE 6 and Mälardalen University. Today we also have our respondent, Sahar Tahvili, obviously. We have the faculty examiner and opponent, Professor Franz Votava from Graz University. We have senior research scientist Shaukat Ali from Similarity laboratory in Norway. And associate professor Brian Nielsen from Aalborg University. And Professor Ann Håkansson from KTH Royal Institute of Technology. So the agenda of today is that the respondent, Sahar Tahvili, will start by giving a short introduction to her thesis. Then the faculty examiner will give his view on the thesis and the strengths and weaknesses of the thesis, and there will be a discussion between the respondent and the opponent. Finally, the grading committee is asked to ask questions on the thesis and discuss this with the respondent. And after that, we open up for questions from the audience as well. And in this final part, also the advisors are invited to participate if they want to. After this, we close the open part of the defense, and the grading committee will meet and make a decision on whether the thesis has passed or failed. And this decision will be communicated by the chair of the grading committee in the coffee room here at Java, where there will be some refreshments and snacks as well. And this concludes the defense, finally. So with that, on behalf of Mälardalen University, I would like to open up the public part of the PhD defense and give the word to Sahar.
Thank you, Marcus. Thank you very much. Welcome everybody to my PhD thesis presentation. As Marcus said, my name is Sahar Tahvili. I'm a researcher at RISE 6 here in Västerås and also an industrial PhD student at Mälardalen University. Today I'm going to present my PhD thesis entitled Multi-Criteria Optimization of System Integration Testing, which has been conducted with a close collaboration with Bombardier Transportation here in Sweden, also Mälardalen University, especially its EASY Research School, which supports us for doing research in the industrial domain in Sweden. For all papers and studies that I'm presenting today, we conducted at least one industrial case study from Bombardier, and at RISE we do usually applied research in the different area of computer science and applied mathematics. Today I'm going to cover the following point. First, I'm going to start with introduction and background. What is software testing and why we need to optimize the testing process? Research goals of this thesis. We conducted some research goals. We tried to answer the research goals in this thesis. And this thesis includes 6 different studies, A to F. And I'm going to just very short present the industrial result and that proposed approach that we used and conducted in this thesis. I'm going to conclude this presentation with, again, some industrial results and also some future direction of our research. So software testing. What is software testing? According to the definition proposed by IEEE standards, software testing is a process that we are trying to detect the hidden bugs in the software product before we release the product to the market. So software testing can be assumed as a critical and important phase in the software development life cycle. And having a better and more efficient testing process is still demanded in both the state of the art, is a hot topic in the research, and also in the companies, the state of the practice. So what happens if we have not a good testing process? Unfortunately, from the beginning, from first day, there is so many catastrophic incidents. We can mention to the Space Shuttle Challenger it happened based on the testing problem. The supplier released the gas tank and they failed during the testing process, but the NASA ignored the warnings and we know what happened in the end. And until today, new problem, we can mention to Samsung Note 7. And according to the news, the total cost that Samsung paid for removing the product completely from the market is more than $5 billion. And it's not just about the cost, it's human lives, and in safety critical system, it makes more sense to having a better testing process. When I'm talking about testing, we need to consider that testing can be performed up to 4 different levels. It depends on the company, depends on the output and other things, but usually we perform testing in 4 different levels. And in this project, we just work with integration testing, which can be performed after unit testing. And when we test different components separately before, we are trying to test the interactions between software modules, between different components. Here I have another example in train system. We have door system, we have brake systems. They tested before, they worked before perfectly. Now we are testing the interactions between these two. For example, if the door is open, the brake should be on in 7 seconds. It's just one scenario. We are testing these interactions between these two. So many scenarios we can design for testing the interaction testings between different components. And when we have a large product like a train with different parts and subparts, so we can, of course, define more scenarios. Usually the number of test cases that we need to test the product can be pretty large. For example, in one project that we analyzed at Bombardier, more than 4,500 test cases is created just for testing the interactions between modules. So it's pretty large, right? And these things makes integration testing even more complicated. It's a complex process compared with other testings level. Until today, software testing can be performed manually, automatically, or semi-automatically. Again, in this project, we just work with manual integration testing. For testing a product manually, we need to have a set of test case specifications. Here I have an example, exported from door system, from Bombardier, again, just to have a better overview about the input of this problem, of this optimization problem. As we can see, there is so many information like test case ID, requirement, standards, platform, and we have here the main important part of the test case, actions and reactions. These two should match with each other. If we got any mismatch between these two, the test step will be failed, and the test case will be failed, and you need to re-execute this test case at least one more time. These texts are written by human testers, engineers at industry, and this one is the input for solving this optimization problem. So we use this one, a large set of these examples. And why we need to optimize testing process? Now we have an overview. Large set of test cases, so little resources, deadline, manual creation of test cases, manual execution of test cases takes time. So we need to optimize this process and having a better, and at the same time providing a better quality of the final product. In this thesis, we try to apply different techniques in artificial intelligence, such as natural language processing, deep learning, machine learning, in order to optimize the testing process. But before that, we define the test optimization problem as a multi-criteria, multi-objective decision-making problem. Criteria in this case, in the testing domain, can be considered as a property. Test cases, properties. You have a large set of test cases. You need to distinguish test cases with each other. What is the differences between test cases? You have a large set. We call it criteria. You can call it test cases properties. And we analyzed, first we started with the state of the art. What is the criteria for test cases? Which criteria, which property is more important? How many properties we have? And then we went to Bombardier. We asked testers, engineers, their opinion about the criteria, test cases properties. And we conducted a list. Here I have 3 examples. For example, dependencies between test cases. which is the most critical criteria, especially in integration testing level. It makes sense. You are testing the interaction between two components, two things in different scenarios, so they can be dependent on each other strongly. There's a strongly interdependency between them. Requirement coverage, another criteria. How many requirements will be covered by each single test case? And you can assume it is a standard. It depends on company and depends on the system that you are testing. So requirement coverage is the second important criteria for us. And execution time. It doesn't matter if you are executing test cases manually or automatically. Anyway, this test case takes time, and you need to have an overview about that. If you have planned to release the product on time, you need to know, based on the test cases that you generated, what would be the required time for running them. So these three criteria are most important criteria for us in these cases. And then we can achieve some goals, like minimizing the total testing time, or on-time delivery on the final product, or cost reduction. You can achieve all three. You can say one of these criteria goal is more important for me, and you can say same thing about the criteria. You don't need to use all of them. You can add or remove. Using this information help us to design main goal, research goal of these theses. So we have one main research goal, providing a method for more efficient testing process in integration level through minimizing redundant failure of test cases based on dependency and maximizing requirement coverage at each testing cycle. So this one is the main goal of this thesis. We divided this main goal to 5 sub-research goals. First, detecting the dependencies between test cases. As I said before, the most critical criteria for us. First research goal. Second, execution time. Estimating the execution time for manual integration test cases before execution. Number 3, requirement coverage. Measuring automatically what is the requirement coverage for each test case. You can see research goal 1, 2, 3 answers 3 main criteria. How we can measure or automatically measure these test cases' properties. Then we go for research goal 4, proposing a decision support system, an automated system which can measure the test cases' properties and ranking them, scheduling them for execution. And in last research goal, we are trying to measure the effectiveness of the proposed approach in terms of cost and time reduction. So this figure shows how the main research goal is divided into 5 sub-research goals and which study answers which research goal. As I said before, we have 6 different research papers in this thesis. And here is the list of the papers, and I'm going to just very short present the papers. In study A, we try to conduct some read some paper in a state of the art. We detect the problem of test optimization. It's a multi-criteria problem. We find some criteria in a state of the art, and we had no idea how we can measure the effect of those criteria on the test cases. We went to Bombardier, and we sent a questionnaire. Very easy, simple questionnaire to the testers, testing experts at Bombardier. We asked them about the effect of the criteria on the test cases. And they answered by using a simple linguistic variable between very low and very high. They had different opinion, of course, and we took an average sometimes. Still, human work suffers from human judgment. We know that, but that was the basis of our study. We had no idea if the proposed approach could be applicable at industry or not. So we sent this one. And on Zefiro project Italy, we asked them, the testers that worked with that project. And they answered for 5 different criteria in this project, in this paper. like execution time, requirement coverage, dependency, execution cost, and fault detection probability. So sometimes test cases can be independent as well. So they said, for example, this test case is independent. There's no test case before this one that you need to execute. You can execute this one independently whenever you want. But sometimes test cases are multiple dependent, like this example. 3 test cases should be executed before this one. We use this information, and we create a dependency graph for test cases, this one. White nodes here represent independent test cases. As I said before, you can execute independent test cases without order. You can check other criteria, but you don't need to take the dependency problem between them. They are independent. The gray node represents single dependent test case, which means just depends on one independent test case. And the black node represents multiple dependent test case. It means you need to execute other test cases before reaching this one. According to our hypothesis, independent test cases should be executed first, and a multi-dependent test case should be executed in the end of the testing cycle. We check the order, the current order. So the red numbers here represent the order that testers at Bombardier took for execution, and the blue number is our proposed approach, just for these 5 test cases. And we check the test records after execution, the results. So here, as you can see, the multiple dependent test case failed 3 times, just because other test cases, which are here before this one, didn't execute it successfully. As soon as they got passed for other test cases behind this one, they got passed for the multiple dependent, the black node test case here. And the total saving hours just for this small amount of test cases is 40 hours. And more than 4,500 test cases you have for testing a project, so you can assume what would be saving time and cost. In study B, we check all test records, all test results for Zephyr project. And we had a plan to develop a decision support system. But again, we didn't know if it's beneficial or we can save money, more money, what is the return on investment, what would the gain if you have such a decision support system at industry. And first, we detect that almost 45% of test cases in the Zephyr project failed just based on dependencies in that project. So 45% of failure happened based on dependencies between test cases. Then we use the well-known formula of return on investment. What would be the gain if any company will use our proposed approach? So testing cost without our proposed approach, without a decision support system, DSS, minus the testing cost with our proposed approach and the cost of our proposed approach. And the cost of our proposed approach is a sum of implementation, training, maintenance, data collection, etc. Before we change our direction to automation, we calculate this value first. By using a Monte Carlo simulation, we propose 3 different versions of the proposed approach: a manual version, a semi-automatic version, and a fully automatic version. As you can see, the value of ROI increased from the first day, which means having a decision support system, even a manual version of decision support system, can save cost and, of course, time in the testing process. These figures help us to decide us to change our direction to automation and proposing a decision support system, automated version of a decision support system for test optimization. First, we started with the execution time, one of the criteria that we have. We design and implement and develop Esprit, our tool, for estimating and predicting the execution time of manual integration test cases. Esprit is a Python-based tool, just because the input of the problem is test cases written in natural language text, and the performance of Esprit is analyzed on 2 ongoing projects, testing projects C30 and BR490 at Bombardier. Coming back to the input of the problem, as I said before, a large set of test specifications. So here we have an example again. Sometimes in a test specification, some timing information is inserted by the testers. Sometimes this comes from requirement, sometimes it's assumption, and sometimes it's real time that they know this activity should be performed in 10 seconds, for example, in a step 3. In a step 4, it's just waiting 20 seconds. So it's still timing value, right? We use NLTK Python. NLTK is a toolkit in Python. We parsed all information in the test specifications. We captured all timing information which was available in a test specifications, and we inserted in our database as a maximum execution time for each test activity. So here is a screenshot of our database that we created, and more than 3,200 test activities until today is recorded in our database. And in max time column, you can see what is the maximum execution time for different test activities. We just captured the critical and important information on each test specification. Like, for example, a verb and a supportive argument. What is the verb? Login. But login what? Login system A, system B, system C. And as you can see, they take different time value. One supportive argument, one verb we choose, and we analyze requirements specification as well, test specifications, and sometimes we check the test results, but still it was some situation that was no timing information available. Then we took the baseline time value, 3 seconds. The reaction time on TCMS, Train Control Management System at Bombardier. This baseline time value, you can change it. In any other system, it could be different. In our case, is equal to 3 seconds. So when Esprit meets a new test specifications, it tried to find a match for different activities. In any case, if Esprit can find a match, we use baseline time value, 3 seconds. And of course, after execution, we have this chance to check the result. If is it detected correctly or not. Coming back to the criteria that we have for test cases properties, as I said several times, that dependencies between test cases is the most critical criteria that we have. 45% of failure between test cases happened just based on the dependencies between test cases. Solving this problem automatically, that was a challenging task for us. How we can detect the dependencies between test cases automatically, then we can avoid unnecessarily failure up to 45% if we can detect it automatically. We had a hypothesis that this dependency should be detected not in the testing level, and we need to check different phases before we go for the testing level. So we check BR490 project at Bombardier again. We open the TCMS platform, Train Control Management System at Bombardier, and we analyze what happened in that platform between different modules, between different components. Like, again, backing to the first example, you're trying to test the interactions between door system and brake system. Inside door system and inside brake system, you have different modules. As you can see here, module 4 receives an internal signal from module 1, which makes this module dependent on module 1 and makes brake system dependent on door system in this example. Until this internal signal is not released, you are not able to test that module in this example. When this signal will be released, when you tested it correctly, fully, and what happened in the testing level, we have the requirements, and we know how requirements are connected to the modules. So first, we detect the requirements dependencies, how many requirements are assigned to different modules. And then we have test cases. And now we know how many test cases are assigned to each requirements. So now we can detect the dependencies. We know now all requirements and all test cases which are assigned to module 4 should be tested after all requirements and test cases which are assigned to module 1. Just we did a strong assumption here, as I said, all test cases. Maybe in the reality is enough with 75% or 85% or maybe it's 100%. We didn't start any study on this part yet. Just because we are working with optimization and efficiency, we are trying to minimize unnecessary failure, and we said 100% now. But in the future, we are going to remove this assumption and analyzing after how many % execution for module 1, this internal signal will be released. That is the future work, and that is our strong assumption that we did in this work. In this figure, figure 5, you can see how problem is complicated. Red nodes represent test cases. Blue nodes represent requirements. First, we measured the requirement coverage. Now we know how many requirements are assigned for each test case. But as a tester, if you want to start the testing, you don't know from which node in this figure you can start the testing. It's very complicated. Where is the first node? Which one is independent, or which one can you execute successfully? It's very complicated. You can't start it. And that's why in the testing level, they got failure. The problem is like that when you are just checking in the testing level. So in this study, we also measured the requirement coverage for each test case. But still, we have the dependency problem. The nice information, the fancy graph is not available every time. Even at Bombardier, we have it just for one project. Still, we need to detect the dependencies, and we have just text. We have just test cases. And we had another hypothesis that maybe the semantic similarities between test cases can provide some clues that we can detect the functional dependencies between test cases. We took 2 projects at Bombardier, BR490 and C30 again, and we used this information as the ground truth. Now we know what is the correct answer of dependencies. We know how test cases are dependent on each other, and we use this one as the ground truth, the correct answer of dependency. But since this information is not available, but still we can compare it with any other proposed approach, but this information is not available, what we have in the testing level, in all companies, we have at least test cases, right? If we have no requirements, no signal information, but test cases you have. And what is behind these red nodes? Test specifications. Some redundant information, of course, but if you remove and just keep test cases, this information is available, and you have it in all testing levels. So how you can detect the dependencies between test cases? By using this information, the only available information in all testing levels. We use a deep learning NLP-based approach, Doc2Vec, and we use test specifications as input to this algorithm. Doc2Vec reads a test specification and provides a data in high dimensional space. Doing a clustering based on the points that we get after running Doc2Vec, we are maybe able to detect the dependencies between test cases. The algorithm measures the semantic similarities by providing a cosine similarity, and here is the results. We use 2 different clustering algorithms, FCM and HGB scan, and we tried just to cluster test cases, which we thought they could be dependent, and then we compared the results with the ground truth. Every single node here represents a test case. When they have the same color, it means they are in the same cluster. Being in the same cluster means they are dependent. And we use 2 different algorithms, FCM and HGB scan, and then we try to compare the results with the ground truth, with the correct answer of dependency, and also comparing the performance of these 2 algorithms. For performance metric, we use a precision, recall, and F-score. The precision is the number of correctly detected dependency over the total number of detected dependency bias. Is a metric that you can calculate, compare with the ground truth. And recall is the number of correctly detected dependency over the total number of existing dependencies between test cases. And using F-score can provide a harmonic relationship between precision and recall. And for HTB-scan and FCM algorithm, we got these results. So as you can see, F-score in HTB-scan has a higher value, and we recommend to use HTB-scan. And degree here means the dependencies between test cases is like two test cases, TC1 and TC2, can be connected by using one shared requirement, 1 to the age. This means degree 2. This goes up to 26. But in the most common dependencies is degree 2 here between test cases. And we got this value, F-score. We need to consider that the maximum value for F-score is 1. So we are 75%. We are trying to increase it. There's different ways that we can do, applying PCA or using different clustering algorithms is some future work that we are trying to do. So using all information that I presented help us to design and implement a tool, a decision support system for test scheduling. A stochastic test scheduling. Why stochastic? You have no idea about the test results. After each execution, the dependency might be changed between test cases. We call it Sortis, our tool for a decision support system, Python-based, for a stochastic scheduling of manual integration test cases. Sortis reads both requirements specification and test specification as input. Sortis detects the dependencies between test cases and also measure the requirement coverage between test cases. Then we go for a scheduling phase. Based on the test results, a new schedule will be provided by Sortis every time. This figure shows a user interface of Sortis. White lines represent independent test cases. Red lines represent dependent test cases. We have the priority number, we have requirement coverage, and execution time. The value of execution time, we use spread, our first tool. In the future, we are going to merge these two tools together. But right now, we are using that one for predicting the execution time of manual test cases. As soon as we get passed for a test case, you can click on this button. This test case will be completely removed from a system, and a new schedule will be provided by Sortis. As you can see, for example, we rank them in this example by requirement coverage. And for example, test case 7 covers more requirements. Test case 8 covers more requirement than the first test case. But this one is a dependent test cases. You are not able to execute it as a first one. Your feasible set that you can rank test cases is here between these independent. For dependent, before you get pass answer for the previous ranked test cases, you are not able to change. But as soon as you get, for example, pass answer for test case 7, test case 8 became an independent test case, and the color will be changed to white. Then you have another feasible set that you can change the order. The performance of Sortis is analyzed on Bombardier again, and on BR490 project, ongoing project at Bombardier. And in these figures, we compared the value of requirement coverage proposed by us and the current value of requirement coverage at Bombardier. So red lines shows the current requirement coverage at Bombardier, and green lines is our requirement coverage. We analyzed 3 different testing cycles at Bombardier. And as you can see from the beginning, we increased that value by using Sortis. And then we checked the troubleshooting time. When one test case fails, right now at Bombardier, it takes 16 hours to cycling back a failed test case to the testing phase. So we checked what will be happened if we rank test cases by sorters compared with the current approach. So you can see we minimize the troubleshooting time. Just because we avoid up to 45% redundant failures based on dependencies, it's not something magic, it's just based on that part. And also comparing the performance of sorters with history-based prioritization. Establish well-known approach in a state-of-the-art and also at companies is very easy to implement and use this approach. In a history-based prioritization, the blue line here, you rank test cases based on the history of failure. If test case A fails first, should be executed as soon as possible. First failed test case should be executed first, right? Then we analyzed failed test cases in the first testing cycle at Bombardier. We ranked them in the second execution cycle by using this blue line. And we compared with Bombardier and ours, both troubleshooting and requirement coverage. And you can see the current proposed approach by Bombardier covers more requirement coverage and less execution time, which means human judgment and human decision still can have a better performance than established method in the state of the art. In this case, maybe in another case, history-based prioritization has a better performance. But in this case, we asked the engineers and they ranked test cases like that, and you can see they have better performance. But so far, sorters performs the best in this situation. And same in the third execution cycle. In the last execution cycle, again, history-based shows the worst performance, both in troubleshooting time and requirement coverage. And Bombardier and we show better performance. Conclusion. Coming back to the main research goal of this thesis, we try to propose approaches for a more efficient manual integration testing process by decreasing unnecessary failure and increasing requirement coverage at each testing cycle. 40% redundant execution cycle is saved by sorters, which leads to 9.6% increase in requirement coverage in one project that we analyzed. And starting this thesis, this study, this research, by using a simple survey for asking testers, people at Bombardier, about their opinion about the test cases properties, to 2 tools can be considered as a second contributions that we did. We have 2 tools today, and these green lines can be detected automatically. So we don't use the survey. We started just with this one to have an overview about the problem, but today we propose 2 tools during these studies. But of course, we are not done. So many things that we need to cover, maybe more after the discussion as well in the future. We have planned to merge Spread and sorters in the future. So when we have a new test case in the system in sorters, all criteria can be detected automatically. So we don't need to use a separated tool. Then we have planned, hopefully, release it as an open source tool for research purposes in the future. The proposed deep learning approach for semantic similarity is implemented separately, but we have planned to merge it with sorters again. Then it doesn't matter which kind of input sorters has. Sorters can find the dependencies, but we need to improve the approach first, but we have planned to add it to sorters. The strong assumption I said before, all test cases depends on all test cases should be relaxed in the future. We are analyzing after how many successful execution the internal signal will be released between test cases. Execution cost and fault detection probability, we have some proposed approach, how we can detect it. Cost can be defined as a function of time. As soon as we have execution time, we can estimate the execution cost, and fault detection probability can be detected by doing some regression analysis on the previously executed test cases. For example, right now we know the brake system has more fault compared with the radio system. and also comparing the performance of sorters with other methods in the state of the art. We just took one just because it was easier to implement and easier to compare. But there is so many other methods like genetic algorithm, and we are trying to compare the performance of sorters, and we are open for changing the algorithm behind sorters if we find better sorting algorithm in the future. But this work could not be done without help and support from Bombardier Transportation. All engineers, especially Ulla Selin, manager at TCMS platform at Bombardier, he helped us so much, and his team, the testers, engineers, testing experts at Bombardier. Without them, we couldn't start this study and we couldn't make it. And also, co-authors of the paper, especially my master thesis student, they helped me so much to make it as a real tool and do the implementation, tool implementation. And also, it's Easy Research School. They supported our research here at Malvern University, and they support industrial research, which can help us to do more research in the future. Also, my supervisors helped me so much, and our manager, Helena, at Rice, and also Petra, my personal manager at Rice, and also all my colleagues at Rice. So with this one, I'm done. Thank you. Thank you.